good afternoon. I hope you all enjoy the lunch. And then, so my title is of the talk is Disinfection of Far-UVC for Airborne Microbes, promising future for bioaerosol disinfection or not. So, just pose some big questions. Is this Far-UVC better than the low-pressure mercury lamps? We all want to know that. And number two, can Far-UVC disinfect well in practical scenario? This morning we heard about a lot of the rooms, hospital classroom, but what I mentioned here may be ventilation ducts. That's why I focus on the high flow rate. Is this a sustainable solution? Is there any harmful emissions? We talked about the ozone this morning. And the last one, we haven't talked a lot so far, is what are the main disinfection mechanisms that different from the 254 nanometer? So this is the content. I try to divide in the four parts. The first one is the Far-UVC versus 254 for particle duct disinfection, followed by disinfection mechanism investigation for inactivation bacteria. Then followed by the Far-UVC to UVA, the wide range of the action spectrum, also for the bacteria and the bacteriophage. Then number four is a little bit for the virus and the modeling work. So this is the setup for the measuring the Far-UVC disinfection efficacy for a particle ductwork. You can see the length is 9 meters. And then, of course, we have the very different form of the light source. This is the flat, conventional 222, and this is the very typical 254. They are in a different form. Then how can I make sure they have the same dose? So that's why I don't put in the duct. I don't put in the duct. I put outside the duct. I put outside the duct, so you can see there's a window. So in that case, I can control the dose by different measurements. But by the way, this is a two emission spectrum for the 254 and the 222. So now here is more clear. I put the source here. So this is a window, so that by adjust the height, I can control the dose. And I measure different points because from the aerosols generated from the right to left, then I need to calculate precisely the dose. It means the time and the intensity. Because the intensity will change along the vertical direction, that's why I need that much of points to get the average intensity. Okay. So in this test, I use a very standard one-pass disinfection efficacy. And then for the bacteria, I quantify CFU. For the bacteria phase, I quantify by TFU, nothing new. And then the UV dose, as I mentioned, is I times T. So I precisely measure the I and the T. Okay, there's a term here called Z values. In different aspects, they have different names. Some water research they call decay, but here I'm using UV inactivation rate constant, okay, or some people call susceptibility constant, okay. The higher of this value means that the bacteria, the microbes or virus will be more susceptible, okay. So here are the results. As we know that when the velocity increases, the contact time decreases. So that's why in general the efficiency decreases. So you can see from here, I test 0.7, 2 to 4. They are quite practical for the real ventilation duct. So you can see all are decreasing, as I mentioned, because the dose decrease. And 0.2 is, you can see that at least from this result, 254 and 222 are doing comparatively well. Okay, that is good news. Now, but you may argue, oh Alvin, why the efficiency only 50%? That is not high. But remember, I put outside the duct. In another test I published, when I put the UV, the same UVC inside the duct, I get 100%. So it means that if you can put the Far-UV222, you may also get very high disinfection efficacy. This one because I put outside. So the set values. So because I can precisely control the dose by adjust the height, right? Because I put the lamp outside, so I can adjust the dose. So in here, the slope represents the set values, okay? And then you can see that here are the general trend later. So carcinogenous greater than Narcissus, greater than E. coli and Epidermis, and then greater than the P22. And in general, the gram-negative set values higher than gram-positive and higher than the P22. Okay. Of course, where some general observation is gram-negative higher than positive, maybe because one of the reasons, not the only reason, because of the thicker cell wall of the gram-positive. Okay. Okay, this is the conclusion for this part. We found out that Far-UVC are efficient and safe for disinfection. The ozone we also measure inside the duct is less than 2 ppb. And you can see that if we can focusizing the length, in this are using one length, right, one source. If you can increase the source, you can really get a very high 1-pass disinfection efficacy. Okay, and that's why I mentioned that we can using multi-lamps. Okay, but multi-lamps, in the later part of the course, I will tell you how to model the multi-lamps. Okay. Okay, part 2. Disinfection mechanism investigation for inactivating airborne bacteria. So in this part, I want to focus on the 222 and I will combine with negative air ions. Okay? I want to see any synergy effect. That's why I can combine both. And then I want to know more about the disinfection mechanism, as I mentioned. So the method is I perform the chamber experimental in the chamber. You will see later. Next slide. And I will using different assays analyze for the bacteria before and after the treatment. It include the lipid peroxidation, superoxide osmosis, safety activity, and the antioxidant activity. Here is the setup. So you can see that I put the source here, the 222, and then these two are the negative ionizer. So I generate the bacteria or the virus using the atomizer, and this is for the collection by the biosampler. So I measure different height at many points inside the chamber. The average invariance is 3.42 milliwatt per cm square, which is much lower than the water medium, and it means it's more reductive. The volume ion concentration I use also is very practical. It's 10 to the power 6 ions per cm. So here is the results. On the left hand side, you can see that the log in activation. Here is just the negative ions. Here, the green one is just the 222. And the blue one is the combined. And then you can see that, well, when combined, it seems that it is larger than the individual. So that's why I quantify by the synergy ratio. I define this synergy ratio. Basically, it's the difference of this bar compared to the sum of these two bars. Okay, so you can see that all these 3 bacteria I test, they have positive synergy ratio. It means that 1 + 1 greater than 2, but depending on the different number, some higher, some lower. Okay, then I also using some assay tests to see what happened on the lipid peroxidation. Now, you can see that this is control, negative ions, and 222, and the combine. You can see for all these three bacteria, we found synergy, right? The individual always adding of these two somehow less than the combined. And also for the antioxidant enzymatic inactivity. This one I measure, you can see here, the white bar is the control, and this is the negative ions, this is 222. So it means that 222 inactivate the enzyme quite good. But if I combine together, it may do better, okay? And I also measure ROS in the intercellular reactive oxidant species. So you can see here, I just not enough time to do all, so I just report on the E. coli. So you can see that for the control, here is the value, and for the negative ions is higher, it means generate ROS, and then for the 222 also higher, but when I combine, another time I see the synergy effect. It means that if you combine different strategy, sometimes you can kill the bacteria faster. And here's the conclusion for this part. Negative ions produce ROS, and then the 222 are inactivating the antioxidant defense in airborne bacteria. And coupling these two may contribute to the synergistic effect. So I want to take this slide to emphasize more on the synthetic disinfection. Why this is important? I always think that some microorganisms may be difficult to be disinfected by the single mechanism. For example, let's say if a bacteria is resistant for the UV, if you just increasing the UV, it's not very effective, right? So that's why if we can find other mechanisms that can combine together, work better, then we can maybe in one day we can make a smaller and more effective device. Okay? In this part, I test Far-UVC and the negative ions, and then I found out that they have synergy. But as not enough, I want to know how much synergy and why we have synergy. And this is the part 3 of the talk. As I mentioned, I try to study from 222 to 365 the UVA spectrum. The objective is to compare the different inactivation rate constant, the set values, for free bacteria and free bacteria phase. I also want to will report inactivation result with respect to the nucleic acid, protein, phosphate absorption. And also importantly, I want to compare how much energy I use per order of reduction. Okay, here is the 6 wavelength I test, the same chamber, but this time no air, just the UV for different spectrum, no air, no ionizer. Okay. Here are the results. So as I'm here, this page shows the result for the bacteria. I test 3 bacteria. So the y-axis is the log, and the x-axis is the UV dose. And because I know the intensity, so at the same time, I can calculate the set value. It's shown here. And this is the result for the bacteria phase. Okay. How about the action spectrum? Okay, now, look a bit complicated, so let's focus on the left-hand side. This is bacteria. This is the bacteria phase. So, in the literature, I have include 3 different absorption curves. One, nucleic acid, the other protein, the third one is the phosphate lipid, so it's also here. And then the inactivation rate are normalized 254, okay? But the absorption normalized 268. And then I have a few findings. For the bacteria, the peak at 268, you can see here, peak at 268. And the pattern follow closely with the nucleic acid. We all know that for the UVC or 254, 268, they mainly kill the DNA. So that's why higher here, very high here. We find that for the inhibitor more strongly than E. coli, even 268, we can see the difference. But not so much different for the 222, all are focused here. And for the bacteria phase is on this side. You can see very different. We have two peaks. One at the 222, one at the 268. Okay, it means that 222 not only kill the DNA, they also have some deal with the lipid and protein. Okay? And one interesting is we have very high value for the pi 6 here. Okay? And then here is the electrical energy per order. As I mentioned, this is important for the practical value. It means that how much energy you use for one log reduction. Now, the good news is 254 is slightly better than 222, but 222 in fact is not bad. You can see here, 222 always is the second. Okay? The reason is the 268, the wavelength is mainly for the LED. And the UVC LED, the efficiency we mentioned this morning is still low. But when the technology advances, it will give better results. And could be improved if the thermal efficiency improves in the future. Okay, this is a little bit for the virus and the modeling work. Here, the top figure is the Western blot analysis for the OC43 for the virus is only, and then left hand side is the spike protein, and the right hand side is the nuclear capsid protein. Okay, the bottom part is for the with the infected cell. You can see clearly that under 222, it's nothing. It's very weak. It means that 222 for this OC43 do much better than 254 and 265. Okay? And finally, for the modeling part, how many minutes I have?
10 minutes.
Okay, thank you. So now, remember, I mentioned set values. Now, set value is very important because we all know that it is very tedious and expensive to do modeling work, to do experiment. If we can model, it means that how much lamp I can put in the air duct, I can get how many efficiency and in how many hours, then it will be perfect. How to do that? We need modeling. But the modeling is not that straightforward because in the air duct we have emissive invadance, means direct. We have defect because the duct can be defective, right? So we have two components. Now I will not go through this. What I mentioned here is what I want to mention here. In the modeling, we need set values. Set values cannot be automatically generated. It's all from us to do difficult experiment to get the set values. Once we have the set values, I can put in this term, then the model can predict the bacteria concentration at different weights. Now, as I mentioned, modeling sometimes is not obvious, especially when the lens geometry are difficult. You can see, if this is only one single lens, it's very easy. You can get empirical solution. But how about if the lens is like this, and how about the lens with different louvre? Then it will be very difficult to model. So, in my group, I have we have a method to model the complicated geometry. You can see the results here. I will not go in detail, but you can see here the modeling and the measurement match quite nicely for different speed, and the disinfection efficiency also match quite nicely. Okay, I'm an engineer. I'm not a microbiologist. So I always ask myself, as an engineer, we want a safe, low initial and operation cost disinfection device. Of course, we need to design high one-pass disinfection efficacy device. The device must handle high flow rate and compact size, otherwise no one will use it, okay? But as a scientist, we want to understand more disinfection mechanism. Why do some microorganisms show synergy, but some don't, okay? And I'm currently developing a filterless air disinfection device, and like this put in the central system or a portable disinfection device. And I need to acknowledge the funding agency, and thank you very much.